Hi, in this video, we want to take a look at conducting local tests for spatial autocorrelation when we're in the situation that we have aerial data. So aerial data is where we have like polygons on the ground, such as neighborhoods, counties, states, countries, etc. And we have data for each of these individual regions, and we want to see for these regions, do we have spatial autocorrelation? Now, after we have that addressed on a global scale, that's the previous video, we want to look at the local tests. The goal of the local test is to find clustering of data that have similar values, and we want to find hotspots that have either greater than their neighbors or less than their neighbors' observations. The examples that we're going to be working through are from Applied Spatial Data Analysis with R, Chapter 9, Modeling Aerial Data. Here's the name of the authors. Here's the website of the book, and you can download the book for free at UCF's website. All right, so let's go ahead and get to it. All right, so global tests for spatial autocorrelation are looking at the local relationships between the values of observations at spatial entities and their neighbors. Okay, so when we work through this, we have to, before we get going, before we do anything, we have to decide which polygon regions, which neighborhoods are neighbors to each other. And then we also have to decide what are the weights when I talk about the the relationship between neighbors. Now, any regions that are not neighbors with each other will have a weight of 0 between them because they don't connect. All right, and so the choice of neighbors and the choice of weights will have a huge impact on our output. So if we make a poor choice, everything that's going to come out afterwards is going to be garbage. So we have to be ready for that. Now, we choose our neighbor format, we choose our weights, then we run our global tests. The global tests are just checking to see, is there something going on somewhere? And now when I talk about the local tests, I'm interested in finding what is interesting here. Where do I have clusters? Where do I have hotspots? And so what we're going to be doing, really how this works out mathematically, is that we're going to take the components, the individual parts that are combined together to give us our global test. We're going to take, if I'm interested in a particular neighborhood, I'm going to take their portion of the global test and pull that out and take a look at it. And so that is how we run through this analysis. So a similar way that you could do this, so think about, so to make this into a little bit simpler statistical test connection, if I do a chi-square test and I see it's statistically significant, that means that there's something going on. I need to take a look at a deeper level. And so what I do is I look at the residuals of the chi-square test, and where I have large residuals, I look and see, hey, what's going on? All right, so here, this is, we're in the phase of that where it's like, what's going on? Let's get, I have a global aspect in that analyzed. Why is there a difference from the null hypothesis? All right, so we want to find clusters, that is observations with very similar regions with observations similar to their neighbors. And we want to find hotspots, that's observations that for regions that are very different than their neighbors. All right, so one of the first things we're going to do, of course, is we're going to visualize what we're doing. So we're going to do a Moran scatter plot. So this is going to be a plot of the spatial data against its spatially lagged values, and we're going to put in the importance. We're going to mark if they're influential, yes or no. And we're going to add a linear regression line to help us visually see what's going on. And we're going to cut up the plane into quadrants. So our x-axis is going to be the variable of interest. Our y-axis is the spatially weighted sums of the values of the neighbors, the spatially lagged values. And we're going to make the plot character to indicate, is this an influential point, yes or no? Then what we're going to do, we're going to take, so Moran's I from the global test is similar to a correlation coefficient. Well, if it's similar to a correlation coefficient, let's go ahead and take a look at the linear equation between the variable of interest and the spatially weighted sums of values of the neighbors. And then just to go a little bit further, let's go ahead and chop up the plane into low low, low high, high low, and high high regions to see if we can visually detect something. All right. And so here we're going to run the Moran plot in the SPDEP package. Here is my data. So the variable of interest are the cases. So this example is dealing with leukemia cases in the state of New York. Now here is the weights that we have. And so to get my weights, I have my neighbor object. So this object defines which regions are neighbors with which other regions. And then for our actual modeling, we need to determine the weights. And there's several styles that we can go with. So I could think of like binary and like regular weighted average as being kind of two ends of a spectrum. C is somewhere in between. And quiet just says, don't give me excess output. We just want the visualization. All right, so now let's go ahead and take a look. And to me, this feels a little bit busy, a lot going on. It's definitely an accurate plot. We have the non-influential points are just a regular circle. And then we have, this diamond with a circle in it for the influential points, and it's the row name is plotted with it. So that way we could go through. Now, you'll notice that the ones with larger, the more extreme X values and the more extreme Y values are coming up as influential. Well, why is that? Well, that really that is that's connecting to how we measure influential points in regular regression. All right, so I'm really not feeling love on this plot. So, and here's that regression line for us. So I went ahead and did a ggplot version. It's not too difficult. So when you do the Moran plot function, it will give the output as a data frame of the points that you want. And it will give the influential measures and stuff like that. So I went ahead and just up here in the code, you'll notice that I saved the outputs here. And so I'm just going to drop that into ggplots. And so I'm just saying the X what the Moran.plot function says is the X, which is the variable of interest, is X. Lagged values as the Y, and then I'm coloring by is influential. The reason why I put color inside the geome point, because if I put it up here, that regression line will get split up among the two types of points, which is we don't really want on this particular plot. And so then I'm just labeling what's going on. It gets a little bit crowded, so I use geom text repel to kind of get some space between. Slapping down that linear regression model with geom smooth, and then here I'm just splitting up the plane into 4 regions. And so here we can see same information presented in a different manner. I think this is a little bit easier to read. All right, so there's a connection between global Moran's I and the linear model of spatially weighted sums of values of neighbors. All right, so what we can do because of that linear regression connection, what we could actually do is I could go through, and after I get the Moran plot data frame out, I could go ahead and drop that, the spatially weighted sums, and the target variable into a linear regression model. And I could say that, to get more insight into what's going on. And furthermore, I could go ahead and take that linear model output and I could put it into the influence measures if I want to get a little bit deeper into this, if I want to get more specific on what's going on. So we have our DF betas, we have our DF fits, covariance, Cook's distance, the hat matrix entries, and we have an indication if it's influential. And this is a base R function. This is not from SP depths. All right, and this I gave the full output, so we're going to scroll through this pretty fast. All right, so now here's the actual value of I for the so this is I sub I. This is well, we're taking this to represent the individual region in terms of Moran's global I. So we have Moran's global I is taken from adding up a very specific calculation for each region. Now we're taking the add-ins of that summation and we're grabbing it for the region respectively. All right, so local statistics can be tested for divergence from expected value. That's basic statistics. Now we have several ways to go about though, because remember, whenever I'm doing hypothesis testing, the assumed distribution is a big deal. It will have a huge impact on the results I get. The distribution I use to get my p-value will can drastically change what I conclude is going on. So we have regular normality assumption. So like typical in statistics when we have convergence in terms of central limit theorem. We can do analytic randomization. We can do a saddle point approximation of the distribution using method of moments, and we can use exact methods. Now, exact methods definitely would be advantageous, but the computation time can grow very large for moderate sized data sets. And so depending on the size of your data, how powerful your computer is, how long you can dedicate to this, that might be okay, that might not. So, and saddle point approximations can also take a long time. And so there's disadvantages to the exact methods and saddle point approximations, but if you want the actual best representation possible, those are the ones to go with. So saddle point approximations and exact methods are more useful to us when we have a smaller number of neighbors for each observation. The normality aspects can be problematic when we don't have enough data points to assume the central limit theorem has kicked in yet. All right, so let's go ahead and visualize the regions with more influence. All right, so what I want to do, I want to go in and I want to visualize the regions with more influence, and I want to indicate, are they low, 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 high, high, low, or high, high. All right, so remember I've got two things going on. So in terms of my target variable, I can have low or high. In terms of the lagged value, I could have low or high in relation to the mean. All right, so let's go ahead and do that. So I'm going to take the cases. So X is the leukemia cases for each of the regions. I'm going to break up that data. I use the cut function, and I'm going to break it up so that we're looking at above and below the mean. So here's the minimum, here's the maximum. These are just cap points. You can also put in negative infinity, infinity here. It'd be a little bit less to read, but a little bit less. The intervals will be less informative because here in this setup, you know what the min and max are. Here we're labeling it, and including the lowest is because if this is set to false, which is the default, the intervals will be half open, which won't work out. We'll miss an endpoint. All right, so let's go ahead and compute the lag on the weights. So here's the weights of what's going on. Here's a variable of interest. And then we're going to, once again, bin these spatial autocorrelated values. Then we'll go ahead and take a look at the cut for the cases. Remember, that's high and low. the spatially lagged values, high or low, modeled values, and then is influential, yes or no. And we'll do interaction to get that going. Now, what we're going to do, I'm going to go through, I'm going to make all the regions that are not influential into one color. And then when we have the other versions, when we have high, low, low, high, or high, high. So I'm interested in the cases of, of leukemia. Low, low, for this purpose, really is not interesting. So I'm not going to change the colors there. And so now we're going to use Brewer palette to set up the colors. Here I've got my legend. And so here we can see the regions that have influence. All right, so when it's green, that means that it's either low influence or it's low, low. Either way, we're not too worried about it. Purple is where we're high, low. So the actual values are high, but the modeled values are low. Orange is low, high. So the observed values are low, but the modeled values are high. And then yellow is high, high. So the observed and the modeled values are high. Okay. And we can see that orange and yellow are tending to come together. And remember that whenever I have a small population, a few data points can make a big difference. And so here, like that's a small region in there, got some small regions in there, depending on population size. So here, when I say small region, that's really by population for this case. So we might, it's just something to be mindful of as we look at this. And I went ahead and just redid the Moran plot with binary weights, and we get a similar output. Remember, if you don't have subject matter knowledge about what's going on, binary is a good choice. All right, so there's several different versions of the Moran local test that we can run. There's the local Moran, which is like the standard way, where I just pass the variable of interest and the weights. We have saddle point approximation, so local Moran saddle point approximation of the distribution. To get that, we can get the exact values as long as the data is not too big. All right, so here we've done the computations in 3 different ways. Once with the assumption of normality, once with, the first one is with randomization because I left that on default. Randomization, one with saddle point approximation, and one with exact. All right, so let's go ahead and figure out what is the overall rate of the entire region and use that along with the population to figure out what is the expected number of leukemia cases in each region. So if I have a constant rate, so let's say this, I'm trying to explore the idea that we have constant rate across the entire studied region. If that hypothesis is correct, then I should see observations close to the population times the rate across the board. And so here you'll notice that we're doing some multiplication. Here we're just getting the weights going. Now here we are rescaling what's going on. Now something about this that's important is that when I work with this, I'm going to make the assumption that we're working with a Poisson distribution. All right, we're dealing with counts, right? And now at this point, I'm assuming that for this hypothesis approach, that we don't have over dispersion. So it's like the standard Poisson distribution. You'll notice that my expected cases are being treated as my expected value and my variance on this step right here. So I'm rescaling everything under the assumption that the expected value is equal to the variance like in the Poisson distribution. Now here I'm going to compute the lag on it, and I take the scale of the cases times the lag. So now, so this is if we have constant risk, this makes sense. All right, so let's visualize the local Moran I values, calculate the standard way, and we're going to use the Poisson assumption for the constant risk hypothesis. All right, so there are some sign changes between borders on the map. All right, so that's interesting. If I have sign changes, that means that a region here and its neighbor, one's going to be positive and one's negative in relation to their expected values. Okay, so I expect a certain value here, but this is above. I expect a certain value here, and this is below. Okay, well, that's a sign that there's something going on locally of what's happening. So let's go ahead and visualize it. So here I'm just setting up the color for everything. Here I'm saying this is the standard calculation, putting it in here. Here is if there's constant risk, putting that column in. Now let's go ahead and plot these two and take a look at what happens. I'm using the SP plot function and the SP package. And so we can see that the constant risk approach is giving us more intense regions than with the standard calculation. Overall, things are pretty similar, but there is a difference. Now, something to be mindful of is if I'm in the situation of over dispersion, then I can have problems working through this autocorrelation approach because I'm making the assumption of the Poisson distribution. So let's go ahead and construct a Monte Carlo test to address the constant risk hypothesis for local Moran I values. All right, so what we want to do, we want to take a look at if under the null hypothesis, we had constant risk and things would be relatively even, in proportion to the region's population. And I want to check, does this make sense compared to my data? Does my data support the point of view that we have constant risk across all regions? Then we'll extract the rank of the observed constant risk Moran's I's for each track and calculate populated value for the number of simulations made. All right, so this approach, in this example, we're going to take a parametric approach to simulating the local values. And we're going to use the expected counts as the parameter to the random Poisson number generator. And now the reason for this, another way that we could approach this in terms of bootstrap Monte Carlo approach is that I could permute the values about all the different locations. But when neighbor counts are very low, when I have very small numbers, it doesn't make sense to do that. It's too, I have like small numbers in my data, like a little bit of change in the leukemia numbers can skyrocket or plummet the proportional value. So therefore, I don't really want to go this way. And doing this, we really would be setting ourselves up to comparing regions that are dissimilar to each other with each other. So instead, we're going to use a random number generator instead of permuting the values at each region. All right, so let's go ahead and get the p-value using the simulations. So I'm going to set the seed so I can repeat this if I want to. My number of simulations, each region, we're going to be working through. And here's the matrix of values. And now here's the expected number of cases I would see if we had constant risk across the board. And I'm going to generate, so for each region, I take its expected number of cases, and then I generate a random Poisson distribution number for that. I do that for all n regions for all simulations. And then I'm going to go ahead and rescale, same way I did before with the raw data. I'm going to set up my weights off of this. And then I'm going to multiply the scale by spatial lagged value. And then I'm going to take the actual observed data along with the simulations, and I'm going to take the rank of the constant risk value, so the observed data version along with the simulation. I'm just going to look at the rank of it compared to the others. And why am I using rank? Because I want to take a little, it's to make it a little bit more robust than to compare actual raw values. All right, so the difference between the simulations and the rank, we'll go ahead and get that. So here, and then, so if it's positive, if the difference is positive, then I'm going to go ahead and take it. If it's negative or 0, I'm going to slap in 0. And so now I'm going to take this difference here, add 1, and then I'm going to take that, divide by number of simulations plus 1. And then I'm going to use the uniform distribution to get the actual p-value. All right, so now I've ran the test in several different ways. I've done saddle point approximation of the distribution. We did the randomization version. So we have regular parametric going on. We have the randomization version. We have the saddle point approximation. We have the exact values. And then we have the p-values from the simulations. And you'll notice that here, the saddle point and standard parametric normal distribution assumption are in the same thing. So I don't have to compute that twice, which is nice. And so now we can actually plot it. Let's take a look at what we've got. So I'm setting up the colors once again. Same color scheme, just making sure it works for the data that's coming up. Using the spplot function. Here is the data that I'm plotting, the spatial data. Here I'm taking the p-values for each of these. Here is the cutoffs for the scale. And so we can see that overall they're pretty consistent with each other. There are differences there. We can see that some of them are more prone to having more darker regions than not. Randomization, something that jumps out at me is that that's extreme red, while the others all have blue. So that's kind of not putting a lot of faith in randomization for me personally. So let's go ahead and zoom into an area of interest. And then I'm just going to worry about these 4. All right, so looking at this, we can see that randomization is different than the others. So let's go ahead and just remove that from this upcoming plot. And so now what we're doing is we're specifying the coordinates that we want to zoom in on. Everything else is the same. And so now in this region, we can see that exact normal and saddle point are producing very similar results. And so, when I see that these 3 are coming up with something very close to each other, that makes me feel like, these are all like pretty consistent. I could probably trust all of them. All right. Well, So from here, we can see, where do we have the extreme values? Where do we have the clusters? And so we can see that we have, the extremes, are red and blue, and we can see that we have, contrasting values up against each other in the neighborhoods, which is very interesting. Why would leukemia be higher or lower on the other side of that boundary? Well, that's all I've got for you. Take care and goodbye.